Okay. Welcome to day 3 of Applications Week in CS144. On Monday, we talked about some of the low-level applications that sort of underpin almost any network connection, the domain name service and the dynamic host configuration protocol. And someone asked what I thought was a pretty good question, which is, like, what are we supposed to get out of this? Should we be able to, like, regurgitate the header formats in an exam or that kind of thing? And that's a good question. And, the answer is no. We're not teaching you these things so that you have to memorize the header formats. I think what we want you to see, I think what we want to do is dispel the mystery. I think we want you to see that this stuff is not mysterious. There is a nice organization of modules that makes the internet comprehensible. And the pieces, things like DNS or DHCP, they exist for a reason. They have a purpose. And I think once you know the purpose, the design of them is supposed to be fairly obvious. It could really only be designed kind of a certain way, reflecting this mentality that we want things to be observable and comprehensible and frankly not mysterious. So I think that's why kind of we're teaching this stuff. Do you have anything to add to that, Nick?
No, exactly. It's understanding and demystifying, really. And as you've probably seen, that surprisingly simple the way in which these different applications use the internet. The applications themselves may be complicated, but the way in which they're using the internet is very, very simple and sort of almost uniform in the way they do it.
All right. Then Wednesday, man, it feels like the week's just flying by. Yesterday, we talked about sort of the history of home networking, starting at that level 1, where it's just you plugging into a modem, and getting up to this level 8, where it's, you have a box in your house that is a Wi-Fi access point that actually does the link layer, talks wireless Ethernet to you, is a network address and port translator, a NAT, and it's a DHCP server handing out these private IP addresses, 10.0.0.0, and it's a DNS server resolving your computer's requests, really resolving your program's requests, and it's an IP router, and sometimes it's the same box is a modem that converts from Ethernet to something that goes long distance over a cable link or a fiber link. So I hope that was a comprehensible lecture. We went all the way from level 1, just like home modem, all the way to level 8, where you're sharing lots of IP addresses with this network address and port translator. And then today we're going to talk about some more applications. We're going to talk about sort of peer-to-peer networking, BitTorrent, and BitTorrent, and we're going to talk about TLS, which is sort of the encryption layer. If we have time, we might flirt with another peer-to-peer system called Bitcoin, but I'm guessing based on the way these lectures have gone and the number of questions we get, we won't have time for that. But we have a whole class in Bitcoin and blockchain systems and that stuff if you want to take it. And maybe we'll stick around a little bit after the class. People want to ask about that. All right, any questions about sort of where we stand? I'm going to resume basically from this diagram. So if there's anyone who feels like this diagram like had you lost, or there's something mysterious here, or you just don't know you don't know where to start, why don't you ask it now and we can sort of recapitulate, and then we can resume from here, and we're going to talk about BitTorrent and peer-to-peer networking.
So Keith, if you can talk about the router just beside the DNS. So given that there is a single IP it received from the ISP, what kind of routing it has to do? What are the different routing it has to do? Does it do internal routing between the 10.0.0 network, or what?
You're asking what does this router do?
Yes. What are the key rules of this, given that it has received only one IP address from the remote ISP?
Yeah, well, let's think about that.
Just routing between these two.
Let's think about. So this router, the routing table, there's an internal network here, 10.0.0, etc., and there's an external network here, 18.241.0.17. So it's possible that I have drawn this in the wrong place, because really the router is routing between the entire external world and the internal world here. Let me think about this for a second. So the routing table on this computer, the routing table is going to send everything to the router, which is going to have some address here, some internal address, like 10.0.0.1. That's going to be the external address of the router. And I guess it'll have some, it'll have some external address here, like 18.241.0.17. 10.241.0.17. So it's possible the router and the NAT really do have to be co-located here on the same computer. So this line is sort of like a notional line. Let's see, how would we do this if these were really separate? I think these might have to be basically the same box. Let's bring them together. And on the inside, it shows up as 10.0.0.1, and it has an interface on the outside 18.241.0.17. How about if I draw it like that? I think that is a great question.
Yep. I would agree with you on that.
Okay, great. Well, that is a great question. Thank you for that. Let's see. Cooper says, what link do modern modems use? Well, that's a great question, Cooper. So on the internal side, it's really just Ethernet. It's like gigabit Ethernet or 10 gigabit Ethernet. And on the other side, it's whatever the long distance protocol is. So one popular protocol is called DOCSIS, which is used by cable modems. And there's also, there's fiber, fiber to the home, looking right like that, fiber, cheap fiber, fake fiber, which is, I guess it's called what is it called? A passive optical network. Is that the right?
Like PON. Yeah.
Yeah. A passive shared optical network.
Mm-hmm.
The companies that have rolled out fiber make a big deal about how it's fiber and it's not copper. But, honestly, even the cable networks are fiber for part of them and copper for part of them. And when they do fiber to your home, it's shared fiber. You're sharing it with everyone in your neighborhood, just like you would share a cable with everyone in your neighborhood. So it's not as big a deal to go from copper to fiber as the fiber companies like to advertise. I mean, real fiber, like the telephone company has, is amazing. But the fiber that you buy when you get from Verizon Fios or something is not that special. In fact, in the beginning, Verizon Fios was not even all digital. There were analog TV channels over Verizon Fios, just like cable. Anyway, I hope that answers the question, what link do modern modems use? Netta Wong asks, where's that router in the blue circle located and who owns it? That's a great question, Netta. This is one of the border gateways for the ISP. This is a router at the border of the ISP, and it's connected to, some other router that probably belongs to the ISP's ISP. And all across the whole internet. So when we talk about the Border Gateway Protocol, BGP, this is a router at the border. So that's where it is. It belongs to the ISP, but it's right on the boundary, and it's connected to a router that belongs to a different autonomous system. Akash says, would a Wi-Fi extender simply be another AP connected to the original AP with a Wi-Fi link between the two? Yes, exactly, Akash. A Wi-Fi extender is just like similar to an Ethernet switch. It's just it only thinks about the link layer, and it just repeats the Wi-Fi packets. Exactly right. Arun says, for inbound traffic to home, routing is done after the NAT translation is done. Yeah, I would say that's true. When you get an inbound, TCP segment here that's destined to 18.241.0.17 from this peer, what the NAT mapping does is it translates it to this peer, 10.0.0.90, and then that gets routed out of the computer. And the routing table is going to say, okay, the 10.0.0.1 interface is over here. So it'll go out on this interface to this computer. So yes, that's exactly what happens. Cooper asks, concerning DNS, how does the computer's etc nsswitch.conf file, which tells the computer how lookup address work alongside the network router's DNS resolver? Okay, that's a good question. That's a good question. So what? let's do it very methodically. In your program, if you make a function call like get host by name or get adder info, that will use a piece of software that's linked into your program in a library, a user space piece of software called the stub resolver. So there's a piece of software in libc that gets linked into your process that is responsible for resolving that domain name. So if you call get adder info on www.keithw.org or stanford.edu or mit.edu, that piece of code running in your process is responsible for finding out the address. But that piece of code does not have all the tools it needs to go out to the root name servers and the edu name servers and the real name servers to actually get the address. All that code does, the stub resolver does, is it asks basically one name server, hey, can you please do this full query on my behalf? So if we look here, can you still see this?
No.
No, you can't. Okay, let me share it.
This went to a black screen.
It went away. Let me share a different thing here. Share screen. I'll just share this one. Okay, there we go. So when your program calls and get adder info, the first thing your program looks at is this nsswitch.conf file. And if it's looking up a host, this will tell your program, the code running in your program in the get adder info function, it'll tell it what to look at. So the first thing the stub resolver will look at is the files. And the first file is this etc hosts. And this just gives a list of locally assigned hosts with the name and the IP address. And here's a name and an IPv6 address. And these are things that libc will return to, as the return of the function call as the answer. So that's the first step happening locally. But if that's not found, then libc will use what they call DNS. And they will go to this file etc. Really, they'll first go to etcgai.conf, which no one ever talks about, and then they'll go to, that's about IPv4 versus IPv6. Then they'll go to etcresolve.conf, and that will tell the resolver, the stub resolver in libc, this is the computer to talk to. Talk to 127.0.0.53 and search these suffixes. So you could search stanford.edu. This is searching something called home. So that will cause your program to send a DNS query to this name server address, which, on a local network can often be the address of your, of your Wi-Fi router, what we call it. Let me bring that up. Can often be the address of this computer here. And then that computer, the DNS server, is going to do the rest of the query on your behalf. So your computer will send one request packet, really, one request to the DNS server. And it's the DNS server that has the list of all the root name servers. And the DNS server will go out to, a.rootservers.net and say, hey, who is www.stanford.edu? And it will tell your DNS server, well, I don't know, but here's who's in charge of .edu. And then the DNS server will go to those machines and say, hey, who's www.stanford.edu? And they'll say, well, I don't know, but here's who's in charge of stanford.edu. And then the DNS server will go to talk to those machines and say, who's www.stanford.edu? And it will say, oh, here's www.stanford.edu. Here's the IPv4 address for that name. And then the DNS server will reply to the stub resolver running on our computer saying, this is the address. And then that's the return value from get adder info. So I hope that answers how the files on your computer interact with the decision of whether or not to go to the DNS server. And then it's really the DNS server that has the list of the root name servers that empowers it to then do the whole query on your behalf. Does that answer your question, Cooper? Is that more than you wanted to know? Okay, great. And then James asks, could you theoretically daisy chain several Wi-Fi extenders together? Yeah, you can. Just like you could put several, you can put several extension cables together. I don't know if you're ever trying to like drill something outside your house. You like one extension cable and then another extension cable and then like a power strip and then another extension cable. You can theoretically do that. The question is, would that impact performance adversely? Yeah, it definitely will impact performance adversely, especially because each Wi-Fi extender can interfere with the previous one. So if they're all on the same channel, only maybe one of them in your house could be transmitting at the same time. But yes, it is definitely possible. James says, I actually learned that daisy chaining cables is very dangerous. Yes, it is. Yeah, no, daisy chaining Wi-Fi access points is not dangerous. It just can hurt the network throughput, but it won't kill anybody. Okay, great. Any other questions about this picture before we move on? Or really about anything we've talked about in this applications week? Okay, great. Well, then let's talk a little bit about peer-to-peer networking. So I want to maybe clean up this diagram. It's a little complicated here. So what I'm going to do is I'm going to maybe take away this computer and let's kind of replace this whole ISP thing with just like a big cloud. You ever wonder why people talk about like the cloud? It's because we don't want to have to put all this stuff in our diagram. So they just draw like a fuzzy cloud to represent like the part of the internet we don't want to have to talk about. That's why it's called the cloud. No joke. Okay. So what I want to talk to you about is peer-to-peer networking. We'll call that level 9, peer-to-peer networking. And this is how systems like BitTorrent work. Systems that allow you to share files across the internet between you and some random person sitting in their home and some other random person sitting in their home, all want to share files with each other. How do you contact each other when you are behind a NAT? How do you make that possible? So let's try and draw the picture here. And instead of Google, we want to make a connection. So let me ask you this. We'll take this, we'll delete this for a second. What happens right now when our computer wants to open a connection to Google? When we open a socket here where the local address is our computer's, what it thinks is its IP address and some random port number, and the peer address is Google's IP address, port 80. This is not a pair of addresses that can actually go out on the internet, because I'll kill the modem here too. It's not important. Why can this not go out on the internet? It's because this address 10.0.0.90, it doesn't really have any meaning. And even if this packet somehow reached Google, and Google's like, okay, I've gotten a SYN segment from 10.0.0.90. Maybe the local address reached Google. So Google says, okay, I'm going to reply to that SYN segment with a SYN segment of my own. And what the heck, I'll acknowledge their SYN segment. So it becomes a SYN-ACK segment. Peer 10.0.0.90, 530.50. If Google sends any IP datagrams to this peer address 10.0.0.90, they will definitely not get back to us because they don't belong to any internet service provider, and BGP won't know where to send them. So it just won't work because this is not a routable, it's not a real IP address. So that's okay, because what does the NAT do when it sees that SYN segment go out? It creates a mapping. It creates a mapping and it says, okay, I see that someone locally is trying to connect from 10.0.0.90 to 53.0.50 to Google IP 80. So I'm going to take the other side of that and I'll create a local side of the mapping that says, okay, I'm going to be Google's IP address port 80. I'm going to pretend to be them. And my peer is this computer. And then there's going to be a remote side of the mapping where I'm taking the real IP address on some port number that happens to be available to connect to the peer, which is Google's IP address. And so what Google sees is it thinks it's communicating not with the real address, but it thinks it's communicating with some routable address on whatever port number it chose. So this is beautiful. This is totally beautiful. But what happens if the connection we want to make is not to Google, but is to somebody just like us? Let's move Google out of the way. And I'm going to take the Wi-Fi access point out of the way too, because this really doesn't matter. So we'll just like draw a line. Okay, so what if on the other side of the cloud is someone just like us, just like that Adele song, someone like you? That's the lyric she sings, right? Someone like you. I think that's the lyric. Okay. Okay, so there's a computer over there, and let's give their router some other address. What's some address that some public address that their router could have from their ISP that we're not going to get confused? Let's just call it 19.12.47.50. So that's the public IP address that ISP has given. Let's take away these NAT mappings. All right. And then this computer can have an address. This computer has an address of 10.0.0.90. And this computer can have an address of 10.0.0.30. It has some other private address that's assigned by its DHCP server. So let me ask you, can this computer connect to Google through its NAT and in the cloud? Yes, it definitely can. Can this computer connect to Google through its NAT and in the cloud? Yes, definitely. We'll put Google on here just so we have it. It can connect to any well-provisioned computer that's actually on the internet. But can these computers connect to each other? Maybe not. Maybe not. And so if we want to share a file with each other, if this person has like the final episode of Game of Thrones and this person really wants it, we can pick a legal example. If this person has a copy of Linux and this person really wants it, a copy of Wikipedia, they can't share it with each other, at least not with what we've learned yet. So let's talk about how that might be possible. Does anyone hazard a guess? Is there something I said maybe in the last lecture that suggests it might be possible? Or let me ask, how could it be possible for these computers to talk directly? Oh, someone says, can you explain why they can't share? Sure, Samak. So how would this computer make a connection to this computer? This computer's address is 10.0.0.90. This computer is 10.0.0.30. They're both private addresses. This computer has a public address of 18.241.0.17, and this network has a public address of 19.12.47.50. But there's no real way for this computer to make a connection to this computer. It could send a packet to this computer to the router, but then how is the router going to know who it's supposed to be for? It's not going to know it's for this computer. It could be, for some other computer. So just connecting to this NAT is like, well, I'm not interested in your Game of Thrones or Wikipedia. So that doesn't get us there. So let me say there's a few different ways we could do it. And let's describe a few strategies. Strategy one, we'll just go back here. No, it's okay. Okay, so we'll call this part A. Yeah, I'll just say them. So this is called, well, we'll just say, yeah. So one way to do it is just to send all the traffic through Google. So there could be a computer here on the public internet that does have a public IP address. And let's give it a nice public IP address, like 4.3.2.5. So one way to do it is that this computer could open a TCP connection to 4.3.2.5, and this computer could open a TCP connection to 4.3.2.5, and whatever bytes this computer sends here are relayed to this one and vice versa. This is called having so strategy A, turn server, or relay or proxy. I'll make that a little bigger. All right, so let's talk about what the NAT mappings look like in this case with this sort of relay computer in the middle.
So do you actually know that 4.3.2.5 is a Google address?
Is it a Google address?
It turns out it is. I just looked it up.
I definitely knew that. Knew that. Okay, so let's talk about what the NAT mappings look like in this case. So we've got, at the TCP sense, we've got this computer thinking that it's opening a connection to this well-provisioned computer. And we've got this computer think it's opening a connection to this well-provisioned computer, which is some like server somewhere sitting on the actual internet, not behind a NAT. So let's talk about what the NAT mappings look like. What is this NAT mapping going to be when we open the connection to the computer? There's a local mapping where it's taking, well, should we just call this Google IP? Let's call it the Google IP. So there's a local mapping from Google IP port, let's just say 80 to, yeah, let's not call it port 80 because we're doing some special traversal thing here. So we'll call it 9000. Google IP port 9000. Okay. And this computer also opens a socket connected to Google IP port 9000 from port 30. We'll just call this port 10,000. Okay. So the local address here is Google IP port 9000. The peer address is 10.0.0.90, port 3050. That's on one side of the mapping. And then what's on the other side of the mapping? The local address is the public address 18.241.0.17. Port could be anything, and the peer address is Google IP port 9000. Okay. And over here, our friend's NAT opens a very similar mapping to, the only thing that changes is these IP addresses. Okay. Now, if these are the mappings, it is definitely true that this computer can send all its bytes to Google, and then Google can send the same bytes back to this computer. This is definitely possible. It's not true that these computers can make a direct connection now. Rachel says, why is it that local is Google and peer is 10.0.0.90? Let's see, where are you talking about, Rachel? Did I screw this up?
Oh yeah, in the on the right-hand side.
In the right-hand side. Okay, so the NAT is acting, well, it's just because of the way this diagram is written, but the NAT is, we should just be clear which side is the private side and which is the public side, really. So on the private side of the NAT, it's pretending to be Google port 9000, and the peer is this computer. And on the public side of the NAT, it's pretending to be its real address. It's using its real address, and the peer is Google. Oh, are you talking about the far left over here, Rachel? So again, on the private side of the NAT, it's making a connection from itself, acting as Google's IP address, to the peer, which is this computer. And then on the public side, it's acting as its real public IP address, and it's connecting to Google. So when any TCP segment comes in from Google port 9000 to this address, the NAT will see it, and it will convert it over to being this pair of addresses, where it comes from Google to the private address of the computer, and then it'll send it out to the computer. So the computer thinks it's talking to Google. Yeah,
That's
is this clear? Is this clear to everyone here? Maybe I should make this even more. Maybe I'll say this is private side.
It's from the perspective of the NAT device rather than from the computer.
Okay, I really want this to be clear to everyone. I don't want to be like, oh, he's rambling about something, I'll watch the video later. If it's not clear, please just speak up, and everyone else will thank you. Okay, I'll take that as a silent affirmation. Okay, okay. So if this is the case, if this is the way the NATs work, then this is basically the best we can do. I mean, can anyone think of a better way? Samak says, since with IPv6 we don't have NAS, does this mean we can directly share files? Yeah, with IPv6, everyone's just on the internet, Samak. You just talk directly. You don't have to worry about any of this BS. That's true. Okay, so the good news is that the NAT doesn't necessarily make a rule like this. Sometimes the NATs make more permissive rules. Oh, okay. So there's something else we could do, an intermediary thing, which would be to explicitly configure a mapping in the NATs. So what if we explicitly configured a mapping that didn't look like this? What if it said anytime that something comes in on port 30,001 from anybody, we want it to go to the local machine at port 53050, no matter who it came in from. So if you configure a mapping like this explicitly, this is called port forwarding. So let's do option B here. It's funny how the letting is never what I actually want it to be. Okay, so option B here is what we call port forwarding, where you log into the website of your NAT and you explicitly say, I want to take port 30,001 on the public interface, and anything coming in on port 30,001, TCP port 30,001, this is TCP specific, convert that to going to the local, my IP address, my computer's IP address, 10.0.90, port 53050. This is called opening a port on the NAT, or port forwarding. And if you do this, now the computers can talk directly. They don't need any Google. Who has to open the connection first? The computer on the right has to open the connection first, but the computer on the right can open a connection. Oops, wrong one. The computer on the right can open a connection all the way to here, and we don't need Google anymore. So let's talk about what does the mapping look like on the right now. Here it's connecting to 18.241.0.17 port 30,001. I hope I got that right. Am I screwing this up here? I hope I have this right. Okay. So the local computer is connecting to the NAT on the left. And that makes a mapping here that says, okay, locally it's pretending to be the NAT, but actually it's talking to this this computer. And then the public side, it's going to use the public IP address here on some port it wants, and it's talking to the, okay, great. So I think this is right. So this computer can now directly open a connection to this NAT. And then this computer will, how does the right computer know that the left's open port is 30,001? Well, they have to agree on that beforehand. This has to be a well-known port number. Just like, how do you know that Google's open port is 80? I hope that answers the question you want to know. This has to be a well-known address. It's the same way that it would know that the IP address is 18.241.0.17. It somehow has to be communicated. But okay, so this computer connects to this computer and to this NAT, and this NAT says, okay, well, something's coming in here on port 30,001. I don't care whom it's from. I'm going to convert it to go to the local machine, the private IP address of the local machine on port 53050. So now these computers can talk directly. So that's option B, is port forwarding. But the only problem with this is that you actually have to like log into your NAT and configure this in advance. So there is an option 3. Okay, I want to be clear. Is this clear about how port forwarding works? Does everyone understand what we just did here?
For anyone that's tried to set up a web server at home or remote desktop management or VNC, something like this, you'd have probably had to do this with a well-known port number opening up on your NAT.
Okay, great. So now let's talk about option C. James says, do we skip the right side NAT entirely? Well, no, James. That's a good question. The right side NAT is still active here. It's converting between the local IP address here, which is 10.0.0.30. It's converting it to its public address, which is 19.12.47.50. So the NAT is still doing that. But this computer is oblivious to that happening. It doesn't know that it's being NATed. It thinks that it has this socket from 10.0.0.30 all the way to the public IP address of this NAT. But the NAT rule is converting it. So if you want, we can draw the line going through the NAT. But as far as this computer is concerned, this is the socket. It thinks it's talking directly to 18.241.0.17. It doesn't know that it's being NATed, just like in that transparent proxy example we had. It's totally transparent to the computer. Okay. So the beautiful thing, which people figured out, is there's an option C here. Option C is called NAT traversal. I guess if we want to be really formal, we'd say NAT. Let's just say NAT traversal. So NAT traversal is just like port forwarding, but it happens automatically. So the procedure is we have to have a NAT that is permissive like this, that makes these kinds of wildcard entries. At least one of the NATs has to be permissive. This is sometimes called a cone NAT or a non-restrictive NAT. But the point is it has to make entries that have these wildcards. It can't make this kind of entry. But if these two computers want to talk to each other, and they have some way to exchange information, which could even be email, it could be any kind of message board, it could be anything, here is how they do it. This computer makes a connection to Google, and it says, or to any well-known server, and it says, hey, Google, what's my IP address and port number? All right, so what happens if this computer opens a connection to Google and it sends a TCP segment with this information, let's call it a UDP datagram, doesn't matter, with this information to Google? what kind of NAT mapping will be created here?
Sorry, when you said, "Hey Google," just now, I just did it again because you know what happened on everyone's phone.
Oh, did it activate your thing?
Activated my
Okay. So let's talk about what happens. So a NAT mapping, let's say we're talking, let's see what we're doing. So NAT mapping would then be created automatically that could look something like this. It could look like this. This NAT mapping gets created when this computer opens a TCP connection to Google. And that the NAT mapping says, okay, anytime that a segment comes in on port 30,001 of my public address, that will be mapped to this local machine, 10.0.0.90, port 53050. And any segments that go out from port 53050 to the internet to anywhere, I'm going to pretend that they came from 18.241.0.17 port 30,001. So this is a NAT mapping that can be created just because a TCP connection got created. And it's the same kind of mapping that gets created when you do port forwarding. But here we're talking about it getting created automatically. So Google then replies, and Google says, I see your connection coming from, what is Google going to say? What does the socket look like at Google's end? Yeah, some of you got it. So what's the port number? So the local address is Google IP 9000, and the peer address is 18.241.0.17 port 30,001. Now 30,001 is really important because that's the public address and public port number of the NAT. So that's what the NAT is making the segments look like. It's not 53050. That's only an internal address. So this is really valuable information because this computer had no idea what the public IP address and what the public port number was until it heard it from someone with an external perspective. So Google says, I see your connection coming from 18.241.0.17 port 30,001. So Google sends this information back to this computer. So this is the first time that this computer learns its public IP address and public port number. And that is now very valuable information because what can that computer do with that information? It can tell this computer over here. So it can say, hit me up for that copy of Wikipedia. I have a temporary assignment of 18.241.0.17 port 30,001. So this computer has learned that it has a temporary lease on 18.241.0.17. It has a mapping, and it can tell this computer. Now, how does it tell this computer? It has to have some way of communicating. It could send an email. It could go through what's sometimes called a rendezvous server. Somehow it has to have a signaling server. It has to have some way of communicating that. But once this computer can somehow get that information to this computer, now this computer can open a socket from its local address to 18.241.0.17/30,001. And that creates a NAT mapping over here, which can be as restrictive as it wants to be. It can still have, it doesn't have to have any stars. And now, just like in the port forwarding example, these computers can communicate. I'll draw it like, I think I picked the wrong tool. So this computer communicates, it goes through the NAT, it goes through the internet, it goes through this NAT, and it goes to this computer. So we have now created a peer-to-peer connection between this computer, and we didn't need any explicit configuration of any NATs. We didn't need to set up any port forwarding rules. All we needed was to have a third computer with a public vantage point that could inform this computer, this is what I see as your public IP address and public port number. And there's a special name for this computer. It is called a stun server. And all the stun server does is it answers questions and it says, I see your connection coming from this public IP address and public port number. And there's a lot of these stun servers on the internet. And in fact, Google does run some. And this is how NAT traversal and programs like BitTorrent typically work. As long as one of the computers is behind a permissive NAT, a NAT that makes these wildcard entries, as soon as the computer makes an outbound connection to anybody, even if it's Google, this mapping is opened up. This port becomes forwarded. And so if the public computer is willing to tell the private computer, this is what I see as your public mapping, that information then becomes the public contact address for this computer, and any other computer on the internet can make a direct connection to that public IP address and public port number, and then they can exchange Wikipedia or Game of Thrones or whatever. So this is called NAT traversal, and this is how many games work. If you want to play a game on the internet and you're playing Call of Duty against someone or Fortnite or whatever, this is how BitTorrent works. This is how Skype works. This is how Google Hangouts works. This is how WebRTC works. This is how many, many systems work that want to make a peer-to-peer connection on IPv4 when people are behind NATs. All right, let's see some questions. Juan asks, why do we need to ask Google? Why can't the NAT just tell the computer? Well, there's no protocol for the NAT to tell the computer, Juan. The NAT is transparent. It's a transparent proxy. So there's no language for the computer to ask the NAT, like, what are you doing to my packets? Rachel asks, what does STUN stand for? I think it stands for Session Traversal Utilities using
NAT.
NATs or around NATs.
Yeah.
It used to stand for something else, but they changed it. Dongzi asks, when the right peer talks to 30,001 of the left side NAT, does it also go to 53050 on the private computer? Yes, Dongzi, exactly, because this NAT translates from 30,001 public address to 53050 on private address. So any segment coming in that was destined for the public address port 30,001 becomes a segment on this private network destined to 53050. Arun says, how soon does the right side have to connect to the NAT? You know, we can actually look at this on Linux, but I think it's like 30 seconds. I think it's like 30 seconds. I wanted to actually get to TLS, so I don't think I'm going to dive into it, but you can actually see these rules on Linux with the contract utility, and it was kind of cool. I think they have about 30 seconds. Nikhil says, how do we know at least one of the NATs is permissive? Well, we don't, Nikhil. It's just that is a necessary condition for this to work. If neither of the NATs is permissive, then they can't communicate directly, and they have to go back to using a turn server, which means sending the data through an intermediary. The great benefit of NAT traversal is that the data doesn't go through an intermediary. It's just sent peer-to-peer. Josh Sheng says, sorry, I'm a bit confused. What's improved compared with port forwarding? The main thing, Josh Sheng, is that it's automatic. With port forwarding, you actually have to log into your NAT and configure it, and you have to have a password and set this up as a human. And then somehow tell the other computer, what your port number is. And NAT traversal just happens automatically. You probably don't even know it. Zoom does that. Well, I don't know if Zoom does this, but programs like Hangouts and WebRTC and video games, they all do this automatically. And some video game is not going to be before you can play our game, you have to ask your mom for the password to your home router so you can log in and set up a forwarded port. No one would play that game. So the benefit of NAT traversal is that it's all automatic. I mean, I can show you what my what it looks like to log into your router here. Let's see if let's see. Can you see my screen here?
Mm-hmm. Yep.
Okay, so if I go to 18.241.0.254, I think it's 1.254.
We can't see the search bar.
Oh, okay, well, I'll move down here.
Thanks.
Let's see. Oh, sorry. Yeah, it's 192.168.1.254. So it asks me for my username and password, and then here's my NAT, adtran, etc. And I guess I go to advanced setup. Here's the setting for NAT. Can you all read this? I'll make it bigger.
Yep, we can
go to NAT. Mm-hmm. And then here is NAT virtual servers setup, virtual server. So this is really annoying. Imagine if you had to do this every time you wanted to have a video conference. That would be super, super duper annoying. This is configuring the port forwarding rules here. So I give external port start and stop and TCP or UDP. So, I mean, I don't think anyone really wants to do this. And so the point of NAT traversal is that all happens automatically, just thanks to having these permissive NAT rules. And this is how most sort of peer-to-peer applications work, including, by the way, Bitcoin and BitTorrent and Hangouts and all these programs that involve communicating between two different computers on the internet, when those computers are going to be in home networks that are behind these NATs and have to share IP addresses. Dominic says, what is the performance gains by using NAT traversal instead of a turn server? I mean, honestly, Dominic, the gain is mostly in terms of money. If you want to send, gigabytes of data through Google, that's really expensive. Typically, these companies charge like 10 cents per gigabyte. So it's very expensive to send data through an intermediary server, like a cloud server. Whereas if you send data directly, I mean, it's basically free. Like that's just part of your internet connection. So it's a huge benefit to send data directly because you're not paying some cloud service 10 cents per gigabyte. I remember when I was I used to consult in the industry, and I consulted for this video conferencing company called High Five, and this is probably highly confidential information. But anyway, it was in an early stage of the company, it seemed to me, and they brought me in, and I started talking about all the state-of-the-art ways to do video conferencing that you could imagine them doing. And all they wanted to talk about was this part of the bill, was the turn server part of the bill. They said if 90% of our customers can use NAT traversal, but 10% of our customers are behind restrictive NATs, then for those 10% of the customers, we're going to have to use turn servers. And turn servers, we got a deal from Amazon Web Services that we can get 11 cents per gigabyte for the data, but Google's only going to charge us 9 cents per gigabyte. So if we move everyone over to Google, we'll save 20% on that part of our bill, and therefore our company will be profitable, and our venture capitalists will invest their next round. And if we don't, they won't. And like this is the level that these video conferencing companies are thinking. And like honestly, that was crazy for me to hear about. But this question about how often does a connection get to use NAT traversal versus a turn server is like, amazingly, it's a major like economic portion of the actual like P&L for these networking applications companies, which I had not appreciated until I consulted for them. That's a very real talk here about the networking industry. Maybe there's more than what you wanted to hear in an undergraduate class. Dominic says, if both sides of the connection don't allow NAT traversal, will video game companies or Zoom own their own turn servers? Yeah, Dominic, they do. But yeah, as I just said, it's a major expense for these companies to operate a turn server. So they're very eager for you to use NAT traversal whenever possible. Dominic says, do companies like Google and Amazon push against NAT traversal because it's a source of revenue? Not that I've heard, honestly. I don't think they've gotten that evil yet. Dominic says, is it still possible to use a torrenting P2P app if your home NAT isn't permissive? Yes, Dominic, as long as the people you're talking to have a home NAT that is permissive. As long as one of the two of you has a permissive NAT, then you can talk peer-to-peer. Okay. In the remaining time, I'd like to talk a little bit about encryption, and this will have to be very brief because we have like 7 minutes. But I want to talk about kind of the layers that what we're building here. So there's different ways to look at these layered models. One way to do it is in terms of the abstractions. So the tower of abstractions that we have at the bottom is like wave packets, like actual packets of waves going through a medium. And on top of that, we build something like Ethernet frames. And on top of that, what do we build on top of that? On top of that, we typically build like internet datagrams. And then what do we build on top of that in like labs 1 through 4? We build like a reliable byte stream. And then on top of that, we sometimes build like an HTTP request and response. And then on top of that, we have like the application, the thing that people actually care about, which is like a web page load. So this is kind of like the tower of abstractions. I made this a little too big. This is like the tower of abstractions that the internet, a typical internet application is built on. Like at the very bottom, there's these wave packets, like actual voltages flowing through the wire. And those are interpreted by the Ethernet card as frames. And then those become internet datagrams. The content of those in internet datagram. There's a reliable byte stream assembled out of those unreliable byte streams. In Lab 0, you made request response on top of that. And a web browser loads a whole page, which often requires many requests and responses. It loads the main page, and that has some JavaScript. It loads the JavaScript loads some images, it loads those. There's a bunch of requests and responses that all load one web page. So this is kind of like the tower of abstractions. A different way to look at it is that we have a tower of protocols that convert between these. So if we wanted to talk about the tower of protocols, what is the thing? Let's see here. I'll move these up one. Maybe we can make these like red. Oh, yeah, now we're really cool, making them red. Okay. So what is the thing that converts between wave packets and Ethernet frames? That's Ethernet. And the thing that converts here is IP. And what's the thing that converts here? What converts between datagrams and reliable byte stream? That's TCP. And what converts between a reliable byte stream and an HTTP request response? That's HTTP. And the thing that converts here is I'll just call it the browser. Okay. So this is typically the stack of protocols or tools that convert between these abstractions. So there's different ways to look at the layers. You could say we have these different abstractions layered on each other, or we could say we have these different tools layered on each other that convert between the abstraction. Ethernet converts from raw voltages on the wire to frames. IP converts from frames to datagrams. TCP converts from datagrams to byte stream. HTTP converts from a byte stream to a bunch of request responses. And the browser uses a bunch of request responses and produces a page load. Okay. So what do we do if we want some security? What do we do if we want to make sure that what a website is telling us is what the real website that we really wanted to talk to wanted to tell us? Because when you did IP and when you did TCP, there's no real assurance that a bad person was not manipulating the contents of the byte stream, right? Like if someone who's eavesdropping on a TCP connection wants to modify the bytes, it would be pretty easy for them to do that. And so in the mid 90s, people decided to modify this tower of abstractions. And instead of putting HTTP directly on this reliable byte stream, they inserted something here. They inserted a new layer. So we have a reliable byte stream, and here we have let's call it a secure byte stream. And the layer that converts between those is called transport layer security, also known as secure sockets layer, SSL. So this is what the layer cake became. So nothing else had to change. They just inserted a layer in between TCP and HTTP, and they inserted an abstraction in between the reliable byte stream and HTTP request response, which was the secure byte stream. So I kind of cringe every time we get these questions about which layer does something belong to? Is it part of the network layer or the transport layer, et cetera? Because the truth is these layer diagrams are kind of descriptive. It's an effort to describe what people have built. And so when we insert something like this that really just converts from one kind of byte stream to another, it's I don't even know what layer you'd say that exactly belongs to. I guess officially it's part of the program. So maybe it's a library linked in the program. Maybe we'd call it part of the application layer. The real thing is to understand kind of this layer cake that we built up. I don't know, Nick, do you agree with that dogmatic view?
That it belongs to as part of the somebody would call it the presentation, but doesn't.
I guess, yeah. I mean, I think my view is that sometimes these names obscure the real meaning. And
exactly. Yeah, they kind of get in the way.
Okay, so let's talk about what this tool does, TLS, that converts from a reliable byte stream into a secure reliable byte stream. That's basically what it does. I guess we have basically 1 minute remaining. What are we doing next? Next Monday is also me. So maybe we'll take this up on Monday. But I want to give you a preview that's what we'll be talking about briefly. And then we have a whole class about security here at Stanford, which I encourage you to take. We're only going to get sort of into the minimal introduction here. But I think the big picture to see is that we have this sort of stack of protocols and we have this stack of abstractions. And what the security part of the stack does is it's just inserted at one place, and it converts between a reliable byte stream into a secure byte stream. Kind of similarly to how, let's say we had maybe this is a user datagram protocol. We could also have user datagrams here, and we could have a protocol like, let's see, am I putting this in the wrong place? Anyway, let me not complicate it further. I've already confused myself. But the point is, TLS is something that converts from one kind of byte stream to another kind of byte stream, just like UDP converts from one kind of datagram to another kind of datagram. But it's totally fine to do this. Someone says, is this how HTTP becomes HTTPS? Yeah, that's totally true.
Exactly.
That's absolutely true. Exactly. So why don't we wish you all a good weekend, and we will pick this up on Monday when we talk about video streaming, and we'll talk a little bit about TLS and the video streaming. And
Happy Halloween, everybody.
Happy Halloween. I'll stick around to answer a few questions if there are any.
Send us your pictures of your Halloween costumes if you like.